Hey everybody, thank you for the kind introduction, and thank you again, of course, to the organizers for everything, and as well as inviting me to give a talk. This, of course, wouldn't really be a GeoFlow meeting if people didn't mention random tensor networks, so happy to be of service in that regard. So this work, Random Tensor Networks with Non-Trivial Link State Spectra, is work that is done in collaboration with Jeff Pennington, Michael Walter, and Freek Woodavine, who's one of Michael Walter's students, who's about to finish his PhD this year, actually. And the paper that is accompanying this is we're like in the very final stages, so hopefully, fingers crossed, it comes out in the next couple of weeks or earlier. But yeah, we're almost done. We're just sort of polishing it up a little bit. And sort of before I move any further, I do want to make one mention that most of the sort of technical legwork and a lot of the technical work in this is really due to Freek. So I just want to make sure that credit is given where credit is due. But OK, so before I really jump into talking about what we did in this paper, sorry, what's going on here? Let me review this random tensor network model so that we all kind of are on the same page about what the title even means. And yeah, OK, I see the green isn't necessarily showing up very well, so bear with me. OK, so what is a random tensor network? So here are sort of I've listed the kind of seminal papers for what these random tensor networks. This is Brian Swingle has like 2 papers, and of course there's this paper from 2016 with a bunch of authors from Stanford. And the idea behind a random tensor network is that first I will hand you a graph. So here is just some collection of vertices and edges connecting those vertices. I will partition the graph into 2 disjoint sets, a bulk set, which I've denoted v sub b here, and then a boundary set, which is v sub this little differential or partial symbol. And after performing this partition, I'm going to make some choice of a state to place on the edges of this graph. And the sort of standard or traditional way to do this is to choose a bond dimension d, and then place a maximally entangled state of rank d on each of the edges. So once I've made this selection, I will look at the tensor product of all of these maximally entangled states, where this tensor product is over all of these edges. And for those of you who are sort of maybe a little more rigorously inclined, this is a little bit of an improper notation, because the edges themselves don't really have Hilbert spaces associated with them. What's really going on is that the edges are, sort of subsets of 2 vertices, and it's the case that every vertex has some Hilbert space of dimension d to the power of however many edges are going into the vertex, the degree of the vertex. But to use nice physicist notation, this is a tensor product over edges of these maximally entangled states that I've chosen for the edges. And this is the random part. For every vertex, I've defined this vertex Hilbert space based on the degree of the vertex. And I'm going to, on each of those Hilbert spaces, choose a Gaussian random vector that lives on that Hilbert space. This is essentially equivalent to choosing a Haar random vector, by the way, on the Hilbert space. They just differ by normalization. So if you want to use Haar random or Gaussian random, doesn't matter. But I'm going to pick some random state on this tensor product of all the vertex Hilbert spaces. And then to get the actual tensor network state, what I'm going to do now is I'm going to use these random vectors and treat them like random projections onto the maximally entangled edge states. So here, all you're doing is you're performing this contraction of these random vectors psi onto the tensor product of all these maximally entangled states on the edges, phi. And you're left with some state that, if you look over here, where I've just rewritten it as an actual matrix, manifestly what you're left with is you're left with some state that lives on the Hilbert space of the boundary vertices. So I've sort of projected out all of the parts of the state that live on the bulk vertices. So the final state just lives on these green vertices out here. And of course, in quantum gravity, the reason why these things are interesting is because these states are known to obey an area law. That is, if I look at some boundary subregion, which I've denoted A, and it's colored in red, which again, maybe you can't see very well, but it is this region A, which is distinctly colored from this other region, which I've called B. If I'm interested in the von Neumann entropy of this subregion, then it turns out that this von Neumann entropy is approximately equal to the length of the min cut. So it is the cut, so it's the min cut for this boundary region, the cut that cuts through the fewest number of edges. And actually, again, maybe you can't see too clearly, but we've actually colored in here the edges that are cut, and times log of the bond dimension. And of course, for many of you sitting in this room, you know that this is extremely reminiscent of the Ryu-Takayanagi formula in ADS-CFT, where boundary subregions on the CFT, the von Neumann entropy of those boundary subregions is proportional to the area of the RT surface, or the min surface that lives inside the ADS bulk. So, in this observation was made in these papers, and people thought, okay, this random tensor network model looks like a really nice toy model for holography. And one of the reasons why it's really nice, and I'll sort of get into it as we go through the talk, is because in this random tensor network model, it's kind of much easier to do exact or rigorous calculations versus trying to handle an actual gravitational path integral. So this was a very exciting model because it kind of captures this area law aspect of the entropies in holography. But in this 2016 paper, another observation was made that maybe sort of dashed the hopes a little bit, which is that not only is the von Neumann entropy equal to this, or proportional to this min cut, it turns out that the entire set of renyi entropies defined for this state are also roughly equal to the same quantity. So in quantum information theory, there is this one parameter generalization of the von Neumann entropy called the renyi entropies, defined by this parameter k. You obtain the von Neumann entropy by taking the limit as k goes to 1 in this expression. And this is these renyi entropies are sort of very useful in quantum information theory because it turns out that these are kind of the right entropic quantities to handle quantum information processing with finitely many states or finite resources. And it turns out that for these random tensor network states, all of these renyi entropies are about equal. And what we say is that these random tensor networks have flat spectra. So the way to think about this is that if all of these, and you can sort of prove this for yourself, or maybe you can see immediately, if all of these quantities are equal to the same thing, then what has to happen is that the eigenvalues of this rho sub A have to all be the same. So the distribution, what we say is the distribution of the eigenvalues, or the spectrum, of this density matrix rho A are about all equal. So the spectrum of these eigenvalues is flat. Now this is a problem if you want to use random tensor networks for gravity, because we know how to compute these renyi entropies in gravity. In fact, the reason why in gravity people are interested in these quantities is because this is much, much easier. These renyi entropies are far easier to compute than this, at least as a direct calculation. So people can do these computations in ADS-CFT, and it turns out that for physical holographic states, they have non-trivial renyi entropies. Their renyi entropies depend highly non-trivially on the value of k. So immediately, it's not necessarily clear then what the random tensor network corresponds to. And this was observed in this 2016 paper that these random tensor networks have this flat spectrum. And I think that at least very early on, maybe just a year or two after this paper came out, there was this thought that, okay, well, random tensor networks were really only intended to ever be a toy model of holography, so maybe this isn't really a problem. They still have this nice area law. We can still do these exact calculations. Maybe not all of these properties will generalize to holography. That's still okay. Very recent work in the last couple years has shown that, maybe to use a cliche phrase, the flat spectrum is a feature, it's not a bug. That the way to think about these random tensor networks is that they are dual to something called fixed area states in holography. So in holography, we can define these quantum states, and we have this area operator that we're interested in that gives the area of the RT surface. You can define eigenstates of this area operator, and it'll be precisely those eigenstates of that area operator, which we call fixed area states, that are dual to these random tensor networks. These fixed area states also have flat spectra, but they're not physical in the sense that you can't actually observe them due to essentially the uncertainty principle, in the same way that I can't necessarily observe momentum eigenstates in regular quantum mechanics. But what you can do is you can stack a bunch of fixed area states together and sort of concentrate the area around some particular value in the same way you do with, say, momentum eigenstates in building wave packets. And then kind of what you get out is going to be a physically observable state, which is like the superposition of fixed area states. So, OK, random tensor networks correspond to fixed area states. And I'll talk a little bit more about this later in the talk. And this equivalence turns out to be highly non-trivial. They're sort of non-perturbative corrections that end up matching on both sides. And so there's this strong belief that, yes, indeed, the kind of right way to think about random tensor networks, at least in the context of gravity, is as these fixed area states. And in my opinion, this is really a kind of where a lot of the progress has been made in terms of understanding random tensor networks in gravity, is in terms of these fixed area states. But OK, most of us in this room are theorists. And we might look at this and say, OK, well, it's nice that we have this fixed area, this kind of fixed area correspondence. But also, it would be really nice to maybe just kind of see what happens if these states didn't have flat spectra, or try to perturb these states so that they didn't have flat spectra, and then kind of see what that corresponds to. And there are a couple of justifications for why you might be interested in doing this. It's been shown in sort of very recent work, like the last year or two, that random tensor networks with non-trivial link spectra are very useful for handling bulk matter in holography. And so it would just be nice if we had this interpretation of random tensor networks as something physical, that we didn't have to resort to calling them fixed area states, which again are not quite physical. And so you can't see this, so it completely doesn't show up here because I made a green circle, so that's my bad. If you are interested in trying to figuring out why this flat spectrum exists, you could quite easily actually trace through your calculation, and you would come back here. The choice of edge state that we made, these maximally entangled states, the reason why the random tensor network state has a flat spectrum is because our choice of edge state has a flat spectrum. Right? The maximally entangled state has all eigenvalues equal, and this itself has a flat spectrum. And so this really is the culprit for why random tensor networks seem to not be physical. And so we get this kind of hand-wavy observation that the spectrum of this boundary state, rho sub A, looks like some number of copies of the link state. Now, being the good theorists we are, we might look at the statement and say, OK, well, this is really only true if the edge state is maximally entangled. What if it wasn't maximally entangled? And actually, this is something that was proposed in the original 2016 paper. They sort of give a very, very quick proposal for how you might modify random tensor networks to not have a trivial link spectra. And the proposal is to simply replace these maximally entangled states with states that aren't maximally entangled and see what happens. And see what happens is exactly what we did. OK, so I mentioned that there's a couple reasons why you might be interested in doing this outside of just theoretical interest. So on the one hand, again, it would be really nice if we could understand random tensor networks as models for something beyond just fixed area states. And I alluded to this. It seems in the past couple years that random tensor networks, or at least fixed area states, for fixed area states, that putting in bulk matter might be is something of interest. When we think about, say, the quantum extremal surface prescription and when is it valid, when do we expect leading order errors. And so putting in non-trivial link spectra in random tensor networks is kind of a natural way to try to incorporate bulk matter into this model. It turns out, so these 2 points here are sort of, in retrospect, points, which after we got the results and then we were interpreting them. But it turns out that the techniques might be useful for other things in quantum gravity, like this replica wormhole program related to thinking about these, again, these sort of corrections that arise when you do these gravitational path integrals. And I'll talk a little bit more precisely about where this relevance comes in a bit later. And a final point, which is very exciting for me, is that it turns out that our results look like a physical realization of this particular quantum information processing task called multipartite state merging, or more precisely, a variant of it called split transfer. And this is actually a protocol that was found by Patrick Hayden and a student of his like 10 years ago. And yeah, it turns out that the random tensor network with non-trivial link states in some sense implements this protocol. And I'll, again, talk a little bit more about that later once I get there. But OK, let me talk a little bit more precisely about what we've done in this work. So here, I've replaced the maximally entangled state on the edges with some arbitrary link state. So here, these lambda sub i's need not all be the same. So now this is some state that has non-trivial spectrum. And I can then take the tensor product over all the edges and call that my link state. So that's one kind of regime that we study. We also study the case where you replace this edge state with what we call a general background state. So recall that this state is defined on the Hilbert space of all the vertices. There's no reason why it needs to be pure and tensor product on all the edges. You could just define any other state on this Hilbert space and do this projection to define your tensor network. Now, this comes with a whole host of problems, which I'll talk about in a bit. But that is a regime that you could study, is you could completely dispense with this structure for the edges and just throw in some other state and see what happens. More precisely, we study a regime which we call the bounded spectral variation regime, which is where the empirical distribution of the eigenvalues for the choice of link state has moments that converge to those of a compact distribution. So maybe it's sort of a bunch of technical words that I just said, but roughly speaking, the idea is that these eigenvalues that show up in the edge state kind of belong to a nice probability distribution, even when I take the asymptotic limit of the bond dimension going to infinity. To study this regime, we use tools from random matrix theory, something called free probability, which is like non-commutative probability. And the starring player is this thing called the method of moments, which I'll talk about in a second. And we also study the case where you have one or more minimal cuts on your network. We then go on to study something called the unbounded spectral variation. Actually, before I move on, I just want to make one more comment on this bounded spectral variation regime. The intuitive way to think about how this regime arises is if you just kind of perturb the maximally entangled link states a little bit. And actually, in an older draft of this paper, we call this regime the almost maximally entangled regime. And then we made the good choice, I think, to change the name. But intuitively, you can get here by just sort of perturbing a little bit away from maximally entangled states. The unbounded spectral variation limit is where, particularly, you want to choose some general background state that doesn't necessarily respect the edge structure on your graph. And now here, you have an issue because there's no, it may be the case that this spectrum of the eigenvalues doesn't converge to anything nice. It might not converge to a probability distribution. The moments might grow unboundedly as you go to infinity. Yeah.
Is it okay to have an intuition where the legs sort of represent the vacuum entanglement in the space-time? I mean, I'm asking because I'm trying to understand what sort of states. So if it's like the vacuum, it should be more like the thermal state rather than maximally entangled. Is that something that you're going to explore here, and in which of these categories would it fit?
Yeah, so I think if it's a thermal state, I think that would probably actually fall under this regime. And in fact, I think most sort of physical states that we think of actually fall into this regime, where kind of the fluctuations of the spectrum kind of will grow in a sort of they might grow like sublinearly or something as you go to infinity, but they grow unboundedly. And so you have to kind of be a little trickier about how you're sort of regularizing these things. This regime is really nice, but again, it really is kind of just limited to maybe small perturbations on the maximally entangled state. But it turns out that you get some really nice kind of looking results, which is why and the proof techniques you need are actually significantly easier than the ones here, which I've mentioned. It turns out to handle this case, we have to throw away all of these techniques we developed over here and use completely different techniques pulled from one-shot quantum information theory and this object called split transfer. So actually in the paper, these two sections are completely distinct and can be read completely without reference to each other, because we use completely different techniques in these two different cases. And this is one of the challenges that I mentioned if you want to try to put some arbitrary state on the Hilbert space of the edges. Because I've thrown away this tensor product over the edges, it's not even clear what a cut on the graph even means anymore, because there's no sort of sense in which we can think about states that live on edges once I use a general background state, right? I don't have this tensor product over all of the edges. It doesn't really respect the graph structure anymore. And so all of a sudden, it's not really clear what cuts on the graph even mean for the boundary state.
It seems like you're generalizing the random tensor networks you started from far, far more than what was motivated just by trying to get something closer to the correct renyi spectrum, right?
Yeah, so I think that rather than, or maybe a good way to put this is rather than trying to get the correct renyi spectrum, it's just how can we perturb or how can we stretch the random tensor network model to get non-trivial link spectra, and when we make these changes to the link states, do our intuitions about how the spectrum of the boundary state and how the spectrum of the cut state are related, do they continue to hold, and in what sense do they continue to hold if we replace these link states with non-maximally entangled states? Yeah?
So when phi is a general background state, in some sense you're kind of, okay, so when the links are local, you're kind of projecting on the local Hilbert spaces. But when phi doesn't have that structure, in what sense can you still think about it as a random tensor network state?
Yeah, that's a very good point. And in a certain sense, you can't, because the graph structure really has no meaning anymore once you use this general background state, which is why this notion of a min cut on the graph as being the cut that goes through the fewest number of edges just has absolutely no meaning at all, and we have to completely reformulate our notion of what a cut is, which is why we end up having to use some aspects of one-shot quantum information theory. Yeah, so it's true that we're still doing these random projections, but it doesn't necessarily have the sort of same PEP state feel that kind of the original random tensor network model has. But yes, we are still doing the random projections, and so in that sense, we still have these random tensors appearing. Yeah. Okay, so. And also as just a caveat, I'm probably going to spend most of my time talking about the bounded spectral variation regime, because that's kind of where a lot of the physical intuition lies, and also to get through this in a reasonable amount of time. I also don't really intend to go into any deep detail in the proofs, because they're all very technical and mathy. Our approach in this paper was to try to do our calculations as rigorously and accurately as possible. So the proofs get very technical very quickly. I'll give some sketches, but I don't intend to sort of go into deep detail. But for the bounded spectral variation limit, we need to define some notation. So here, I've just sort of have notation for the various distributions that we're interested in. We're interested in the empirical distribution of the edge state spectrum. We're interested in the distribution of the cut state, which is just sort of the product of the distributions of the edges that are being cut. And we're interested, of course, in the distribution of the boundary state. And we're going to be interested in the so-called kth moments of these distributions. The particular tool, the theorem that we find in this regime is that if there exists a minimal cut for this boundary region A, then our intuition from the original random tensor network setting holds in pretty much the same way, that the spectrum of the boundary state will converge to the spectrum of the cut state for the case of a single cut. If there's exactly two non-intersecting min cuts, and I'll have a picture in the next slide so you can kind of see the situation I'm discussing, it turns out that the spectrum converges to something that has this form. I have a bunch of symbols here. This MP is the so-called Marchenko-Pastor distribution of parameter 1. And this little box times is something called the free product. This is a object that arises in free probability, which I mentioned is kind of this non-commutative version of probability. I won't go into any details about what these things are in the talk. But roughly speaking, you can think of the Marchenko-Pastor distribution as just being a kind of like random distribution. It's just the source of randomness. And the free product is a kind of special multiplicative convolution that's defined for non-commutative probability spaces rather than the sort of standard commutative ones. And so what does this statement mean? This means that the spectrum, when you have two competing min cuts, converges to a sort of multiplicative convolution of the spectrum on the two competing cuts convolved with some sort of like randomness. And it will turn out that it is precisely this randomness that gives rise to the sorts of fluctuations we see when we do fixed area calculations in holography. So I'll just pause here for a second since I'm kind of glossing over like tons of details in this if people have any immediate questions. Yeah?
So when you have two cuts,
yeah.
So is this answer for the case when they have the same length? Or they don't have?
Yeah, OK. So again, I guess you can't really see what's going on here. But the case of two cuts, this is an example. So suppose the region I'm interested in is this like disconnected, these two disconnected regions, which I call A. And we sort of have two competing cuts in the sense that here I have two disconnected cuts that define the min cut for A. So this is like the disconnected phase in like holography. And this is competing with a different cut, A2, which kind of connects these two disjoint regions. So this is sort of like a connected phase. And so the case with these two competing cuts, physically you can sort of think about it as the case where you're kind of near this disconnected, connected phase transition in holography, if you like that image. And again, sort of the result is that the spectrum sort of looks like this multiplicative convolution plus some randomness thrown in. And how am I doing on time, by the way?
So you have, let's say, 10 minutes.
10 minutes, OK, gotcha. OK, so I will speed through this a little bit. Again, I don't want to necessarily go into any of the nitty. Oh, yeah, sorry.
Do you have the same gamma A for renyi? You have the same minimum cuts for all the renyi?
So the gamma A, sorry, what do you mean by like the same gamma A for all the renyis?
Well, for example, compared to compute the renyi 2 and versus renyi 3.
I see. Yeah. So it'll be the same cut. Yeah.
What's the reason you have the same cut?
So the way we're defining cut in this case is on the graph structure. Like we're just saying this is the particular cut that has boundary given by has one of its boundaries given by this boundary region I'm interested in, and it's the cut that like goes through the fewest number of edges while still having this boundary. So it's sort of defined independently of the like state.
I think you will get for different renyis, higher renyis, you will get the higher renyis of the bulk state, right? With a regime defined by a cut. And I think if you are not choosing the graph spectrum, just a generic state, then the minimum you need to pick out the minimum by varying.
Yes, so that's exactly right. Particularly for the unbounded case, that's exactly what we have to do. But it turns out that in this special case, where kind of the graph structure is still, where we can always refer to the graph structure to define our cuts for us, it turns out that we still have this convergence in the asymptotic limit. But your observation is totally correct, particularly when we dispense with the graph structure. That's exactly what we have to do. You have to sort of look at how these cuts are varying. So in this particular case, again, I'll just sort of speed through the key tools that we use. course, the starring player is the replica trick. For those of you who are already sort of familiar with random tensor networks, the idea is that you can kind of rewrite the moments of the boundary state, the distribution of the boundary state. You can rewrite these moments as a partition function for like a classical spin model. And we will use something called the method of moments. And I think some of you who are already familiar with this can see where this is going. So here we've defined a way to compute the moments for a spectrum. Here we're going to use a technique that says that there are certain sets of distributions which are completely defined by their moments. So if I hand you a probability distribution satisfying some set of conditions, here this is a bound on the growth of the moments, then the distribution is completely determined by its moments. So if I hand you another distribution that also satisfies these properties and it has all the same moments, so for example here, I say that the moments of this distribution mu converges to those of this distribution nu, then in fact the distributions themselves will converge to each other. And then finally, we're going to need this concept of geodesics on the symmetric group, or the group of permutations. The particular thing the particular distance function we're using in defining these geodesics is something called the Cayley distance, which is roughly speaking, or actually not even roughly, exactly speaking, is the number of transpositions you need, so two element swaps you need to go from one permutation to another. And the key property, of course, is that this is a metric and therefore satisfies the triangle inequality. And I won't necessarily go through all of these steps in the sketch in the interest of time, but the slide is included for those of you who are going over this later. The key point to make here is that notice that when you compute the moments using the replica trick, that in this sum over configurations in this partition function, you have this factor of the Cayley distance appearing in this exponent here. And so what that means is that the configurations that will dominate this partition function are precisely those configurations that are minimizing this Cayley distance. And it turns out that the configurations that minimize the Cayley distance are those that I stated earlier. In the case of one cut, it's just the configuration that's given by that single cut. And in the case of the two cuts, it turns out that the moments have this sort of multiplicative convolution type appearance. But really, all that we're doing is we're saying, OK, we're computing the moments using this replica trick spin model formalism. We are extracting the leading order behavior. So at leading order, this is what the moments look like. Then we're showing that, OK, the variance in these expectations that we've computed also vanishes in the asymptotic limit. And so then we conclude, OK, in the asymptotic limit, the moments of the boundary state spectrum converge to those of the moments of the cut state the cut state distribution, sorry. And then by the method of moments, conclude that the distributions themselves will converge. And so again, it turns out that pretty much all of our intuitions hold for this case from the original random tensor network model, that the boundary state spectrum is given by the cut state spectrum, even when you perturb the edge states a little bit. And
I have a question. This one?
Yeah.
Question?
Yes.
So you average over this, over the random tensors.
Yes.
This rho A here, is it normalized?
Yeah, so that's a really good question. The rho A is normalized. The rho A is chosen to be normalized on average, but it turns out that you don't. Yeah, so you don't need that the rho A is completely normalized, like exactly. You only need that it's normalized on average, and that.
The way I thought the way you arrived at it was to project. So you start with degrees of freedom in the bulk, and you project them with random projectors, right?
Yeah. So you can. Sorry.
Right. So then you lose normalization. So you have to renormalize somehow.
Yeah.
That gives you some randomness in the denominator. So what I'm worried about, there is another set of replicas I thought you need in order to average.
So
normalized.
When you choose the Gaussian random vectors to do the projections, you can set the the variance of those so that the final boundary state is, the trace of it is 1 on average in expectation.
So, but that's only on average. And so I think Huda is saying if we choose the states to be normalized for each random realization, then we would need to divide those by some normalization to the power k. And then if you do a replica trick for that, we need to introduce more replica.
Yeah.
Um,
Even I'm very confused how it can be on average, because each projector removes one normalization. So, maybe you prepare it such that it will be on average.
Well, the distribution, I think, yeah, the fluctuations are small.
Oh, I see. Well, it depends if maybe in the d to infinity. Yeah.
This is a very good point, but is it okay if I can get back to you like after the talk, perhaps, so I can speed through the rest of this? Sorry. Yeah, I just know I'm like really short on time. But okay. I just make sure that I want to get to this point about why we might be interested in this from a gravitational perspective. So I mentioned earlier that there has been this sort of non-perturbative equivalence observed between single tensor random tensor networks and fixed area states, in the sense that sort of the non-perturbative corrections that arise when you have competing minimal surfaces are identical for fixed area states and for these single tensor random tensor networks, or just single random tensors. So in a sense, we have sort of generalized that observation to the full network setting. And this subpoint B here, in this sort of lovely paper from Don Meroff, and I think they're 2 of his students, they show that you get these kind of order 1 fluctuations in these fixed area states when you have 2 minimal surfaces that are competing with each other. And we can show through this sort of random tensor network computation that those fluctuations are due to that Marchenko-Pastor distribution that I mentioned earlier, that there's this sort of random distribution that is convolved with the distributions of the cuts, and that gives rise to these order 1 fluctuations. And finally, it turns out that this technique of representing the distributions as this free product actually precisely reproduces and generalizes this sort of resolvent method for understanding the sum over replicas in JT gravity that was given in this, this lovely Stanford paper with Jeff and Steve Schenker and others. That the resolvent and this diagrammatic argument where they sum over replicas and things like that. It turns out that this is precisely equivalent to this free product structure that we defined, and moreover that this free product structure we've defined sort of in a certain sense generalizes the method that was found in this paper. So really, maybe just to summarize, the contribution itself isn't necessarily that there's some novel insight in gravity, but more so that the calculations that we have kind of are able to reproduce and in a certain sense generalize previous calculations done in gravity. And this is kind of the approach that we sort of took in this paper, because the paper was already really long and really mathy, that we actually discussed gravity very little in the paper. And that really our goal in writing this paper was to present a series of calculations and techniques that are valid for random tensor networks, and then our hope is that maybe some people will be interested enough to try to figure out the gravitational applications of these computations. But some other sort of interesting points to mention is that in a sort of very recent paper from last year, Xiaodong and Michael Walter computed this entanglement negativity in random tensor networks and holography. It turns out you can use our results as well. So our results you can sort of think of as maybe not even saying as much about the random tensor networks themselves, but something about the replica trick for random tensor networks. And so quantities that you compute using the replica trick for the random tensor network, you can also apply our formalism to the case where the networks don't have these maximally entangled link states. And so you can apply literally exactly the same methods they use in this paper to compute the negativity. You can apply our results to then use their techniques to compute the negativity in random tensor networks that have non-trivial link states in this sort of nice bounded regime. And finally, just again to mention, this is really, in a certain sense, a natural way to implement a non-trivial spectrum in random tensor networks. And now, again, you're restricted to spectra that obey this sort of nice this nice boundedness property where the moments converge to this to the spectrum, but it is kind of a nice way that you can introduce this, and again, it allows you to reproduce some previous results in gravity. And sorry, I'm probably like out of time, right?
Yeah.
Okay, so I just want to super briefly mention, just because there was a question about this. I didn't get to this part of the talk. The problem, if you then decide, okay, you say, you know, I want to use any state. I want to include bulk matter in my random tensor network, and I'm not okay with working in this very kind of limited regime. I want to use general background states phi, not just like these tensor products over edges. You quickly run into a problem that min cuts don't necessarily, on the graph, don't necessarily mean anything anymore because the edges don't necessarily mean anything anymore. The edges are just there to define dimensions of Hilbert spaces. That's it. And so the answer for how to handle this problem is to completely throw out everything we did before and reformulate the notion of cuts in terms of these things called recovery isometries and one-shot entropies. And for those of you who are familiar with this kind of very recent progress in quantum error correction in holography, you'll know that in holography there's this equivalence between the RT formula and min surfaces and entanglement and wedge reconstruction. And this also holds in a certain sense in random tensor networks, where min cuts can be defined by the parts of the bulk for which there exist good recovery isometries that allow you to recover the state on the bulk. And so we said, okay, well, why don't you just, this lets you dispense with the notion of edge cuts and allows you to define cuts purely in terms of what can be recovered. And then very, very recent work from Jeff Pennington and Chris Akers has shown actually this is a good formulation for generic quantum codes. That in generic quantum codes, these so-called quantum extremal surfaces exist, even for codes that don't have geometric interpretations, as long as you're thinking about these one-shot entropies. And that if you think about one-shot entropies and recovery isometries, you can define quantum extremal surfaces for any code in terms of subsystems that can be recovered, for which good recovery isometries exist. And that's precisely the kind of thing we do. I'll just sort of speed through these slides. I won't really talk about them. We get this nice theorem about recovery being bounded by this sort of renyi 2 conditional entropy that kind of bounds the quality of the recovery isometries that you're allowed to have. By the way, it turns out that this statement is really the statement of multipartite state merging that Patrick found over 10 years ago in this protocol called split transfer. You have to, here's another very scary slide, which I didn't really intend to talk about. But the idea is that what you want to do to define cuts is instead of defining cuts in terms of like edges that you're cutting, you're defining cuts. You have to sort of vary your cuts to find a cut such that the smooth min entropy of the cut is larger than the smooth max entropy of other cuts. And that this sort of difference between the min cuts and the max cuts, by the way, this slide is here really more for completeness so that people going through the slides later can look through it. It turns out that this difference in min and max, smooth min and max entropies of your cut turns out to be a bound on how well you can recover the spectrum of the, or how close the spectrum of the cut state and the boundary state are related. So it turns out that if you define, so that we define cuts in terms of recovery, or rather cut minimality is now a spectrum, which is defined by how the accuracy of the recovery isometries that exist on the cut. And based on that accuracy, it allows you to bound the closeness of the spectrum of the edge states and the boundary state. It gets even more complicated when you go to multiple cuts. Here, I mentioned earlier that you have to sort of do some regularizations to make sure everything is kind of well defined. This is really kind of like a central limit theorem, which for those of you who are sort of familiar with the technical statement of it, is in a certain sense a statement about regularization of distributions, sums of distributions. And it turns out that you get this sort of maybe intuitive statement that when you have two cuts, the spectrum of the boundary state kind of picks out the minimal parts of each of the two competing spectra to form its own spectrum. So more precisely, when you sort of try to compute expectations, you should be using the you kind of at every point choose whatever distribution gives you a minimum when you're computing the expectation. And this is precisely the result that was found in this, again, this paper from Don Mayerolf and what I assume are two of his students, where they find that for for holographic states that have two competing min cuts, that is precisely the entropy that you should expect. You expect to find an entropy that is given by an expectation over the minimum of the two areas, and that's exactly what we find in random tensor networks. And here, again, I just sort of mentioned split transfer. Again, split transfer is just this cool information protocol. The idea, sort of more generally speaking, is that the random projections on random tensor networks can be considered to be like random measurements. And so protocols in quantum information theory that use random measurements to implement them, which are a lot actually, you can in a certain sense interpret them in the setting of random tensor networks because we do this random projection, which you can consider as this large-scale simultaneous random measurement. And then finally, I'll just leave my wild speculations for future work up here. The point being that we still have a lot to learn about the connection between random tensor networks and gravity. There's this sort of cute little cycle about people making observations of gravity, us doing, or then other people, not us, but other people doing rigorous calculations in the random tensor networks, which then leads to observations in gravity, which then encourages rigorous calculations in random tensor networks, and so on. And so I like to think about what we did here as sort of this part of the cycle, and then hopefully as a future direction, people will then find some nice application or observation in gravity for how, or rather what these tensor networks with non-trivial link states represent in a gravitational setting. For those of us who have been in this field for a while, we know, of course, that most of our work is just realizing that quantum information theorists had figured everything out already, like years ago, and then we're just kind of massaging it to make it work for gravity. That's also the case here with the split transfer and sort of thinking about these min cuts as recovery. Patrick figured it out, over 10 years ago already. Maybe not in the same language, but it's really just sort of multipartite state merging. And again, that's also, I think, mounting evidence in very recent work that this kind of one-shot entropy state merging framework is kind of really the right way to think about the quantum information aspects of holography. And finally, that random tensor networks themselves are still quite young. There's a lot of math techniques that might be interesting or useful, a lot of ways you can perturb the model, and I'm happy to sort of talk about any of these after the talk. Thank you. Yeah.
So the criteria that Chris and Jeff had worked out for these they came up with a prescription for min and max entanglement wedges, right, based on some smooth conditional max and min entropies. And that didn't sound quite like what you were saying there. It didn't sound like you were defining two different entanglement wedges that were the analog of the min and max entanglement wedge here. Is that right?
Yeah, so I'm not exactly sure if that's the correct interpretation, but that might be because I haven't looked at those papers in a while. Are you talking about sort of the way we redefined our min cuts?
The way you were using the min and max entropies seem to be different. First of all, these weren't conditional entropies, right?
So these quantities are not. So what we show is that originally you bounded in terms of this like conditional entropy, and we can then show that this quantity itself, with some caveats about the state you're applying it to, can then be bounded by this quantity, which is not the conditional ones. But if you like, you could replace this condition with the previous one. It just turns out that this condition is a bit easier to work with because it's not conditional. But you can like.
Should I not expect to get something analogous to the min and max entanglement wedge here? In other words, some region that I can reconstruct everything, and some region where I can at least reconstruct something, and some region where I can nothing.
I think intuitively that makes sense to me, but I don't have like a concrete answer as to whether or not that is like a rigorous statement that we can make. But intuitively, that sounds right to me in terms of kind of how well you can reconstruct things in kind of the space that lives between a min cut and competing cuts.
Any other questions for Newton?
Yeah.
Like as someone with no intuition for this.
No, it's okay.
So if I think about like a very degenerate case of just having a single bulk site,
Yes.
and is there still a sharp distinction between your sort of two classes of deformations from the maximally entangled edges?
Yes. So it turns out that a single bulk tensor with two boundary vertices is actually a very good model for what's going on, and it's actually the reason why in holography, this observation of equivalence between fixed area and random tensor networks can kind of be boiled down to an equivalence of a single random tensor with two boundary regions. And it turns out, so this is sort of a generalization of what's going on, but the same intuition will actually continue to hold. And we mentioned this in our paper very briefly. There's this kind of folklore result about Haar random state, bipartite random states, where like the spectrum converges to a Marchenko pass-through distribution in the asymptotic limit, which is, if you recall, exactly what we found in the other case. So yeah, basically, yes, all of this still will hold, and the intuition kind of transfers over between the network and the single tensor setting.
So if no other questions, let us thank